On a spring morning in 1940, a British civil servant named Donald Coleman Bailey sat at his drafting table in the War Office, sketching what would become one of World War II's most critical innovations. Outside, Britain was reeling from Dunkirk. German forces controlled Western Europe. The prospect of eventual return to the continent seemed remote, yet planning had to begin. The problem before Bailey was deceptively simple: how to get tanks, trucks, and troops across rivers when existing bridges had been destroyed. Traditional military bridging equipment was cumbersome, slow, and required specialized skills. The British Army's standard heavy bridge components weighed tons and needed cranes for assembly. German forces had demonstrated the importance of rapid river crossings during their blitzkrieg campaigns. Polish, French, and British defenders had demolished bridges as they retreated, but German engineers had overcome these obstacles with pontoon bridges and rapid construction techniques. Britain needed something better, something that combined strength with speed, that could be operated by ordinary soldiers without engineering degrees. Bailey's revolutionary insight was this: a bridge should be built like a child's construction set, with identical panels that soldiers could assemble by hand, without cranes, without welding, without specialized skills. Within months of the first Bailey Bridge deployment in 1942, British and American forces could span a 60-foot gap in under 2 hours. By war's end, these bridges had crossed rivers from Normandy to Burma, enabling advances that would have otherwise stalled for weeks. Field Marshal Bernard Montgomery would later declare the Bailey Bridge one of the 3 most important technological developments of the war, alongside radar and the Douglas DC-3 aircraft. Military engineers in the early years of World War II faced a problem that had plagued armies throughout history. Water obstacles, rivers, streams, canals, flooded areas, created natural defensive lines. Retreating forces destroyed bridges behind them as standard procedure. Advancing armies then faced a stark choice: find another crossing point miles away, attempt dangerous river crossings under fire, or spend weeks building a new bridge while offensive momentum died. The mathematics of the problem were straightforward but unforgiving. A typical infantry division required constant supply, ammunition, fuel, food, medical supplies, replacements. An armored division consumed even more. Supply trucks needed bridges, tanks needed bridges, artillery needed bridges. Without bridges, an advance halted at every water obstacle. Traditional military bridges required substantial time and resources. A permanent bridge needed surveying, foundation work, and construction that could take months. The process involved detailed survey of the river crossing site, design of foundations suitable for local soil conditions, excavation and construction of abutments and piers, fabrication of structural steel components, transport of heavy materials to the site, assembly using cranes and specialized equipment, riveting or welding of connections, installation of decking and railings. Even under ideal conditions, this process required weeks. Under combat conditions, it was often impossible. Temporary bridges offered faster deployment but had severe limitations. Pontoon bridges, made of boats or floats lashed together and covered with planking, could be assembled more quickly but couldn't support heavy loads. The German Panzer IV tank weighed 25 tons. The British Churchill tank weighed 40 tons. The American M4 Sherman weighed 30 tons. Standard pontoon bridges buckled under such loads or required so many pontoons that current swept them away. Fixed truss bridges could handle the weight but required massive components. The British Army's standard heavy bridging equipment included steel girders weighing 35 tons each, connection hardware requiring specialized tools, foundation components requiring excavation equipment, assembly requiring cranes or lifting equipment. Moving this equipment to the front required substantial logistics, rail transport to forward railheads, then truck transport to the crossing site. Assembly required skilled engineers, specialized equipment, and considerable time. A competent engineer company might need 3 to 5 days to erect a 100-foot span capable of carrying tanks. The situation became critical after Dunkirk in June 1940. The British Expeditionary Force had evacuated from France, leaving behind virtually all its heavy equipment. Britain faced the prospect of defending against German invasion, then eventually returning to the continent. The army needed equipment that could keep pace with mobile warfare, equipment that could be mass-produced, transported easily, assembled quickly, and operated by soldiers with minimal training. Donald Coleman Bailey was born on September 15, 1901, in Rotherham, Yorkshire, England. His father worked as a clerk. The family was solidly middle class but not wealthy. Bailey showed early aptitude for mathematics and mechanical problems. He attended Rotherham Grammar School, where he excelled in mathematics and physics. After secondary school, Bailey studied at the Sheffield Technical School, later Sheffield Hallam University, earning qualifications in civil engineering. This education was practical and focused. Sheffield was an industrial city, and the technical school trained engineers for factories and construction firms. Bailey learned structural analysis, materials science, and practical design. He did not attend Oxford or Cambridge. He had no connections to Britain's military establishment. He was simply a competent engineer with a methodical mind. Upon completing his education, Bailey worked in various civil engineering positions. The economic difficulties of the 1920s and 1930s limited opportunities, but he gained experience in structural design and construction. By 1928, he had joined the War Office as a civil servant, working in the experimental bridging establishment based in Christchurch, Hampshire. The experimental bridging establishment was a small organization tasked with developing military bridging equipment. The staff consisted of civil servants, engineers who worked regular hours, drew government salaries, and approached problems methodically. It was not a glamorous posting. There were no dramatic deadlines, no urgent crises. The work involved gradual improvements to existing equipment, testing of new materials, and preparation of manuals for field units. Bailey's work through the 1930s was competent but unremarkable. He contributed to incremental improvements in standard equipment. He prepared technical drawings. He supervised tests. He was, by all accounts, a quiet, systematic engineer who did his work thoroughly but without flash. When war began in September 1939, the experimental bridging establishment's mission gained urgency. The phony war period, the months of relative inactivity between September 1939 and April 1940, allowed time for equipment development. Then came the German offensives of spring 1940. Norway fell in April. Denmark fell in a day. On May 10, Germany invaded France and the Low Countries. By June 4, British forces had evacuated from Dunkirk. By June 22, France had surrendered. The rapidity of German success shocked British military planners. German mobile warfare, the Blitzkrieg, had overcome defensive positions that military experts had considered formidable. One element of German success was their engineers' ability to overcome water obstacles quickly. While their equipment was not dramatically superior to British equipment, German doctrine emphasized aggressive, rapid bridging operations that maintained offensive momentum. In this context, Bailey began thinking about radical improvements to bridging equipment. What was needed was not a better version of existing bridges, but a completely different approach. The challenge was this: design a bridge that could span 100 feet, carry 40 tons, be assembled by ordinary soldiers without cranes or welding equipment, use components light enough to transport in standard trucks, and be erected in hours rather than days. Bailey's breakthrough came from observing how mass production worked in British factories. He had seen how Ford Motor Company's assembly line methods had been adopted by British manufacturers. The key to mass production was standardization, identical components that could be manufactured in any properly equipped factory, assembled by workers with minimal training, and combined in various configurations to meet different needs. Bailey applied this thinking to bridge design. Instead of designing a bridge for a specific gap, which would require custom calculations, custom fabrication, and custom assembly procedures for each river crossing, he would design a single standardized panel that could be combined in different configurations to span any gap and carry any load. The panel that Bailey designed measured 10 feet long and 5 feet high. It was constructed as a truss, a triangulated framework of steel members welded together. The truss pattern was a classic Warren truss configuration, with diagonal members alternating in direction. This pattern efficiently distributed loads while minimizing weight. Each panel weighed 570 pounds. This weight was carefully chosen. 6 men could lift 570 pounds with effort but reliably. Lighter panels would have required thinner steel, reducing strength. Heavier panels would have required more men or mechanical assistance, complicating field operations. The 570-pound weight was the sweet spot between strength and portability. The panels connected with steel pins that dropped through holes in the corners. Each corner of each panel had a precisely machined hole. When two panels were placed side by side, the holes aligned. A steel pin dropped through the aligned holes locked the panels together. The pins were 1.5 inches in diameter, made of high-strength steel, and featured a simple locking mechanism. A split pin inserted through a hole at the top prevented the main pin from falling out. No bolts, no welding, no special tools beyond a sledgehammer to drive pins home and knock them out for disassembly. A soldier who could swing a hammer could assemble a Bailey bridge. This simplicity was deceptive. Each panel was a carefully engineered structure, and the pin connections were precisely designed to handle enormous loads. But from a soldier's perspective, assembly was straightforward. Bailey designed the system to be infinitely expandable. The configurations worked as follows. Length panels connected end to end. Want to span 60 feet? Use 6 panels. Want to span 120 feet? Use 12 panels. The panels created a continuous truss structure with uniform load distribution. Height panels stacked vertically. A single height bridge used 1 row of panels. A double height bridge stacked 2 rows of panels, one atop the other, creating a deeper truss that could span longer distances and carry heavier loads. A triple height bridge stacked 3 rows. Width multiple bridges built side by side. A single width bridge used 1 row of panels across the width. A double width bridge placed 2 rows side by side. A triple width bridge used 3 rows. Traffic could use 1, 2, or all 3 lanes depending on needs. The combinations created a matrix of capabilities. Single, 1 panel high, 1 panel wide, span up to 30 feet, carry 40 tons. Single, span up to 60 feet, carry 40 tons. Double, span up to 120 feet, carry 60 tons. Triple, span up to 220 feet, carry 100 tons. The system was elegant because the same components created all configurations. A military unit didn't need different types of panels for different situations, just more or fewer of the same panels. Bailey's second major innovation was the launch mechanism. Traditional bridge construction required building the structure in place, with workers positioned over the river during assembly. This exposed engineers to enemy fire and required access to both banks. Bailey's solution was to assemble the bridge entirely on the near bank, then push it across the river. The bridge would cantilever out over the water, extending from the near bank toward the far bank, until it reached across the full span. The problem with this approach was that a truss bridge, when cantilevering, experiences enormous stress at the point where it extends out over nothing. The bridge wanted to dive nose first into the river under its own weight. Bailey's solution was the launching nose, a lightweight steel framework that temporarily extended the front of the bridge during construction. The launching nose was essentially a long, light truss section that attached to the front of the bridge being built. It was designed to be much lighter than the bridge itself, with minimal strength, just enough to handle its own weight. When attached to the bridge, the launching nose shifted the balance point. Instead of the bridge tipping forward, the extended length distributed loads so the bridge could cantilever across the gap. The launch process worked as follows. Engineers positioned steel rollers near the river edge. These rollers would support the bridge as it was pushed forward. The first panel was positioned on the rollers, with the launching nose attached to its front end. Additional panels were added at the back, connecting to the previous panel with pins. After each panel was added, the entire bridge assembly was pushed forward on the rollers. Soldiers operated hand winches that pulled the bridge forward incrementally. As the bridge extended over the river, the launching nose reached toward the far bank. The bridge remained level, supported by the rollers on the near bank. When the launching nose reached the far bank, it was positioned on the prepared foundation, typically a timber crib or existing bridge abutment. Engineers removed the launching nose and installed the final components: end posts, ramps, decking, and railings. This mechanism meant that assembly happened in a safe area behind the riverbank. Soldiers weren't exposed while working over water. The only moment of vulnerability came when positioning the completed bridge on the far foundation, a process that took minutes rather than hours. Bailey completed his initial designs in late 1940. He submitted them to his superiors at the experimental bridging establishment with a simple proposal: build a test bridge and see if it works. The initial reception was skeptical. Senior military engineers had decades of experience with bridge design. Bailey's concept looked too simple. The pin connections seemed insufficiently robust. The launching mechanism appeared unlikely to work for longer spans. Several reviewing officers suggested that the design was interesting but impractical. Bailey persisted. He had performed the calculations. The mathematics supported the design. In early 1941, authorization came to build a prototype. Bailey supervised construction of the first test bridge at Christchurch. Workers fabricated panels in a local workshop. On the test day, soldiers from a local engineer unit assembled the bridge while senior officers observed. The test succeeded. The bridge went up quickly, faster than observers expected. Load tests followed. Trucks drove across. A tank crossed successfully. Engineers measured deflections and compared them to calculated values. The measurements matched the predictions. The design worked. More tests followed through 1941. Engineers built bridges of different configurations. They tested the launching mechanism with longer spans. They measured assembly times under various conditions. They tested disassembly and reassembly. They evaluated how weather affected construction. By late 1941, the British Army was ready to adopt the Bailey Bridge. The War Office placed orders for production. British factories began tooling up to manufacture panels, pins, and associated components. The British Army's Royal Engineers began training on the new equipment. The Bailey Bridge system relied on industrial mass production. Unlike traditional military bridges, which were essentially custom-built for each site, Bailey bridges used identical components manufactured to precise specifications. Panel production required skilled metalworking, but not extraordinary capabilities. A typical panel manufacturing process involved steel selection. High-strength structural steel was cut to length for each truss member. The steel met specific strength requirements, yield strength of approximately 35,000 pounds per square inch. Member preparation. Each steel member was cut, drilled for connections, and prepared for welding. Precision was critical. Holes had to align exactly when the panel was assembled. Welding. Skilled welders assembled the panels, joining the various truss members into the final 10-foot by 5-foot framework. Weld quality was crucial for panel strength. Quality control. Each completed panel underwent inspection. Critical dimensions were verified. Welds were examined for defects. Sample panels from each production batch underwent destructive testing, loaded to failure to verify they exceeded strength requirements. Protective coating. Panels were painted to prevent rust. While paint seems mundane, corrosion protection was essential for equipment that might spend months exposed to weather. Packaging. Panels were bundled for shipment, typically in sets that corresponded to complete bridge configurations. British production centered on several facilities. The main plants were located in industrial regions with existing metalworking capacity: Birmingham, Sheffield, and other cities. Production ramped up through 1942 and 1943. By 1944, British factories were producing over 100 complete bridge sets monthly. Component standardization meant that production could expand easily. When demand exceeded British production capacity, the design was shared with American manufacturers. The U.S. Army Corps of Engineers evaluated the British design in 1942 and adopted it enthusiastically. American production began in 1943. U.S. manufacturers made minor modifications to suit American manufacturing standards and material specifications, but the core design remained Bailey's. Factories in Pennsylvania, Ohio, Michigan, and other industrial states established production lines. American industrial capacity was enormous. By 1944, U.S. production exceeded British production. Combined Allied production reached over 200 bridge sets monthly by late 1944. The standardization extended beyond panels to all components. Transoms were crossbeams that connected panels across the width of the bridge. They came in standard lengths to match single, double, or triple-width configurations. Stringers were longitudinal beams that ran the length of the bridge, supporting the deck. They came in 10-foot sections to match panel length. Decking consisted of steel or timber planks that formed the roadway. Steel decking, made of corrugated steel planks, was standard for permanent installations. Timber decking, heavy wooden planks, was common for temporary bridges, as wood was easier to source in forward areas. Ramps connected the bridge to existing roads. They came in adjustable configurations to match varying ground levels at bridge sites. Hardware included not just the main pins, but also smaller fasteners, cable, and tools. Everything was standardized and packaged in kits. The logistics of component supply were straightforward. A bridge unit, a complete set of components for a specific bridge configuration, was defined precisely. A 60-foot single-double bridge required 12 main panels, specific quantities of transoms, stringers, and decking, launching nose assembly, foundation components, hardware kit. Supply officers could request bridge units by type. Depots stored components in standard configurations. Transportation requirements were calculable. A 60-foot bridge fit on 3 2.5-ton trucks. Larger bridges required more trucks, but the mathematics were simple. The British Army's Royal Engineers began training on Bailey equipment in 1942. American engineer units followed in 1943. The training curriculum emphasized the simplicity of the system while ensuring soldiers understood critical procedures. Basic training covered component identification. Soldiers learned to recognize panels, transoms, stringers, and other components. While standardization made this straightforward, proper identification was essential. Using wrong components could cause bridge failure. Assembly procedures. Soldiers practiced connecting panels, installing pins, and building bridges in training areas. The repetition built muscle memory. After sufficient practice, a soldier could drive a pin home with a few precise hammer blows. Launch operations. Soldiers learned to operate the rollers and winches used for pushing bridges across gaps. Timing and coordination were critical. The entire crew had to work in unison. Safety procedures. Bridge construction involved heavy components and potential for injury. Training emphasized safe lifting techniques, proper use of tools, and situational awareness. Advanced training covered site survey. Engineer officers learned to evaluate bridge sites. How wide is the gap? What are the soil conditions? What load must the bridge carry? These assessments determined which bridge configuration to build. Load calculations. Officers learned to calculate required bridge configurations. Published tables simplified this. An officer could look up the span and required load capacity and find the appropriate configuration. Foundation preparation. Soldiers learned to prepare bridge foundations. In ideal conditions, existing bridge abutments could be reused. When necessary, engineers built timber cribs, box structures filled with rock, to create suitable foundations. Supervision. Officers learned to supervise construction crews efficiently. A well-organized crew could complete tasks in sequence with minimal wasted motion. By mid-1943, Royal Engineer companies could routinely erect a 60-foot bridge in under 2 hours. American engineer battalions achieved similar speeds. With practice, times improved. Some units erected simple bridges in under an hour. The Bailey Bridge's first major combat deployment came in Tunisia in late 1942 and early 1943. British and American forces were pushing east across North Africa, while German and Italian forces retreated. The terrain featured numerous wadis, seasonal riverbeds that were dry most of the year but flooded during winter rains. Traditional military planning assumed wadis could be crossed easily when dry and forded when carrying moderate water. But North African winter rains created flash floods that turned wadis into raging torrents. Existing bridges had been destroyed during earlier fighting. The Allied advance depended on rapid bridging. Royal Engineer units employed Bailey bridges extensively. A typical operation proceeded as follows. Reconnaissance teams moved ahead of the main force, identifying crossing points. When they found a demolished bridge or impassable wadi, they radioed back with dimensions and site conditions. Engineer units calculated requirements and moved forward with appropriate components. Upon arrival, engineers surveyed the site precisely and prepared foundations. Typically, the existing bridge abutments were intact, stone or concrete structures that had supported the original bridge. If abutments were damaged, engineers built timber cribs as replacements. Assembly proceeded according to training. Soldiers unloaded components, positioned rollers, and began connecting panels. A British engineer company, at full strength about 200 men, could erect a 60-foot single Bailey bridge in approximately 2 hours under ideal conditions. Under combat conditions, working at night, under occasional artillery fire in adverse weather, Construction took longer, but 4 to 5 hours was typical. The bridges performed well in North Africa. Several factors contributed to success. Speed, rapid bridge construction kept the advance moving. German rearguards destroyed bridges expecting to delay Allied forces for days. When bridges reappeared in hours, defensive plans collapsed. Reliability. Bailey bridges handled North African conditions well. Dust, heat, and occasional rain didn't compromise the steel components. Bridges remained serviceable under constant heavy traffic. Maintainability. When damaged, by occasional German artillery fire or by accidents, Bailey bridges could be repaired quickly. Damaged panels could be replaced without rebuilding the entire bridge. By the end of the North African campaign in May 1943, Bailey bridges had proven themselves in combat conditions. Allied commanders gained confidence in the system. Production accelerated to meet anticipated demand for future operations. The Italian campaign, beginning with the invasion of Sicily in July 1943 and continuing up the Italian peninsula through 1945, provided the most demanding test of Bailey bridge capabilities. Italy's geography, mountainous terrain, numerous rivers, narrow coastal plains, created countless bridging requirements. German defensive strategy in Italy relied heavily on water obstacles. The Wehrmacht established defensive lines along rivers, the Volturno, the Sangro, the Rapido, the Arno, and dozens of smaller watercourses. As German forces retreated northward, they demolished every bridge systematically. Allied forces advanced through a landscape where virtually every significant river crossing had been destroyed. Bailey bridges became essential infrastructure. British Commonwealth and American engineer units erected hundreds of Bailey bridges throughout the Italian campaign. The bridges ranged from small structures spanning mountain streams to major bridges crossing significant rivers under combat conditions. The Sangro River crossing in November 1943 exemplified Bailey bridge capabilities under difficult conditions. The Sangro, in eastern Italy, was approximately 100 feet wide with steep banks. German forces had destroyed all bridges and established defensive positions on the north bank. Allied planners needed to cross the river quickly to exploit a temporary advantage. Royal Engineers planned a double-double Bailey bridge, 2 panels high, 2 panels wide, spanning approximately 110 feet. The construction would happen at night to avoid German observation. Components moved forward under cover of darkness. Engineers had surveyed the site during daylight, calculating requirements precisely. Construction began after dark. Engineers worked by minimal light, enough to see components but not enough to attract German artillery. Soldiers moved with practiced efficiency. Panels were positioned, pins were driven home, the bridge extended gradually across the dark water. German artillery fired occasionally, but counter-battery fire from Allied guns suppressed most interference. By dawn, the bridge was complete. Allied troops and vehicles began crossing immediately. The bridge had taken approximately 7 hours to erect, longer than training speeds, but acceptable given darkness and enemy fire. The structure carried heavy traffic continuously for weeks, enabling the advance north. Mountain crossings presented different challenges. In mountainous regions, rivers flowed through steep gorges with limited space for construction. Engineers often had to build approaches, temporary roads leading to bridge sites, before bridge construction could begin. One notable example occurred in the Apennine Mountains in early 1944. A river flowed through a gorge with near-vertical walls. The gap was only 40 feet, but the gorge was 80 feet deep. Engineers couldn't build a bridge at river level. The approaches would be impossibly steep. The solution was to build the bridge higher up the gorge, where the walls were less vertical. Engineers constructed temporary roads zigzagging down each gorge wall to bridge level. They then erected a single Bailey bridge across the narrower gap at mid-height. The resulting structure allowed vehicles to descend one side of the gorge, cross the bridge, and ascend the other side, a solution that would have been nearly impossible with traditional bridging equipment. Extended operations demonstrated Bailey bridge durability. Unlike temporary pontoon bridges, which required frequent maintenance and were vulnerable to flood damage, Bailey bridges remained serviceable for extended periods. Some bridges erected in Sicily in 1943 remained in use through 1945, carrying constant heavy traffic. Maintenance was straightforward. Periodic inspections identified loose pins or damaged components. Damaged panels could be replaced. Engineers simply knocked out the pins securing the damaged panel, removed it, installed a new panel, and secured it with pins. The entire repair took hours, not days. The invasion of Normandy in June 1944 and the subsequent advance across northwest Europe required extensive bridging operations. While Normandy's geography initially limited bridging requirements, the landing beaches had no major river obstacles. The advance inland brought engineer units to rivers where all bridges had been destroyed. Normandy hedgerow country featured numerous small streams and drainage channels. Most were narrow enough that Bailey bridges weren't required, but some needed bridging. Engineers used small Bailey configurations, single bridges spanning 20-30 feet, to maintain road networks. As Allied forces broke out from Normandy in late July and August 1944, bridging became critical. The Seine River crossings in late August required major bridges. Engineers erected multiple Bailey bridges to handle the enormous traffic, entire armies moving across limited crossing points. The Rhine crossings in March 1945 represented the climax of Allied bridging operations in Europe. The Rhine River was a formidable obstacle. Width 300-500 feet at major crossing points. Current strong and variable with changing water levels. Depth too deep for fording or standard pontoon bridges. Defenses. German forces had fortified the Rhine extensively. All bridges across the Rhine had been demolished. Allied forces needed to establish crossings to invade Germany. The most famous crossing occurred at Remagen on March 7, 1945, when American forces captured the Ludendorff Bridge intact. But the damaged bridge collapsed on March 17, killing 28 American engineers. Even before the collapse, American engineers had begun constructing Bailey bridges near the captured bridge. The Remagen Bailey Bridge was a massive structure, a triple configuration, 3 panels high, 3 panels wide, spanning over 1,000 feet. This was one of the longest Bailey bridges constructed during the war. The construction required over 300 main panels, massive quantities of transoms, stringers, and decking, multiple engineer battalions working in coordinated shifts, approximately 72 hours of continuous construction. The completed bridge carried enormous traffic, tanks, trucks, artillery, all the vehicles of multiple divisions pouring into Germany. The bridge operated continuously under full load without significant problems. Similar crossings occurred all along the Rhine in late March 1945. At Wesel, British engineers erected multiple Bailey bridges. At various points, American engineers built bridges to support different army groups. By early April, numerous Bailey bridges spanned the Rhine, carrying the full weight of the Allied invasion force. The Rhine crossings demonstrated several important capabilities. Load capacity. Triple Bailey bridges could carry the heaviest Allied tanks. Even when loaded with columns of vehicles, the bridges remained stable. Speed. While major Rhine bridges took 3 days to erect, this was remarkably fast for structures spanning 1,000+ feet. Traditional bridging would have taken weeks. Reliability. Once completed, Rhine bridges operated continuously. They required minimal maintenance despite carrying constant traffic. Scalability. Engineers built as many bridges as needed. Production had scaled up sufficiently that component supply wasn't limiting. The Pacific Theater presented different challenges from Europe. Terrain ranged from jungle to volcanic islands. Weather included monsoons, typhoons, and relentless humidity. Rivers flooded dramatically during rainy seasons. Burma saw extensive Bailey bridge use during the British Indian reconquest in 1944-45. Burma's geography, dense jungle, mountain ranges, major rivers, created difficult conditions. During monsoon season, rivers became raging torrents. During dry season, they were more manageable but still required bridging. British and Indian engineer units erected Bailey bridges across the Chindwan River, the Irrawaddy River, and numerous smaller watercourses. The bridges enabled supply lines through terrain that would otherwise have been nearly impassable to heavy vehicles. Tropical conditions tested materials and men. High humidity promoted rust despite protective paint. Engineers conducted frequent inspections and applied additional rust-preventive coatings. The steel components held up reasonably well, though maintenance requirements exceeded those in European theaters. Jungle conditions complicated construction. Dense vegetation had to be cleared to create bridge approaches. The heat was debilitating, soldiers working to assemble bridges in 100-degree heat and 90% humidity tired quickly. Construction times were generally longer than in Europe, though experienced units still achieved respectable speeds. The Philippines campaign in 1944-45 required extensive bridging. American forces landing in Leyte and then Luzon found that Japanese forces had demolished bridges throughout the islands. Engineer battalions landed with invasion forces, bringing Bailey components ashore as soon as beachheads were secured. One notable operation occurred during the advance on Manila in early 1945. American forces needed to cross the Agno River on Luzon. The river was approximately 200 feet wide with strong current. Japanese forces had destroyed all bridges and established defensive positions. American engineers planned a double-double Bailey Bridge. They brought components forward at night to avoid Japanese observation. Construction began before dawn, proceeding rapidly. Japanese artillery fired at the bridge site, but American counter-battery fire suppressed most interference. By afternoon, the bridge was complete and American armor was crossing. The bridge served as a main supply route for weeks, enabling the advance on Manila and subsequent operations in northern Luzon. Airfield construction in the Pacific utilized modified Bailey Bridge designs. Engineers needed to create temporary runways and taxiways on islands where Japanese forces had destroyed aviation infrastructure. Wide Bailey configurations, 4 or 5 panels wide, created platforms capable of supporting aircraft. These airfield bridges weren't spanning gaps, but rather creating level, load-bearing surfaces over rough terrain or bomb-damaged areas. The Bailey panels' strength and modularity made them ideal for this application. Air forces established advanced bases using these temporary surfaces, then gradually replaced them with permanent construction as time permitted. As combat experience accumulated, engineers developed variations on Bailey's original design. The basic panel remained standard, but specialized components emerged for specific situations. Extra-long spans were achieved through innovative techniques. The standard double-double configuration could span approximately 120 feet. For longer spans, engineers used several approaches. Intermediate supports. For very wide rivers, engineers placed intermediate supports, either pontoons or temporary piers, mid-river. This effectively created 2 or more shorter spans rather than one very long span. Suspension cables. For some applications, engineers added suspension cables to reduce the load on the central span of the bridge, allowing longer clear spans. Reinforced configurations. For the longest spans, engineers used quadruple height configurations, 4 panels stacked vertically, creating extremely deep trusses capable of spanning 250-plus feet. Heavy-duty configurations appeared for the largest loads. The M26 Pershing tank, introduced in early 1945, weighed 46 tons, heavier than the Sherman tank that had been standard. Engineers designed reinforced Bailey configurations specifically to handle Pershing crossings. Floating Bailey bridges combined Bailey superstructure with pontoon supports. These designs worked for very wide rivers where conventional Bailey spans would be impractical. The pontoons provided intermediate support at regular intervals, typically every 30-40 feet, while the Bailey panels created a continuous roadway. A floating Bailey bridge functioned almost like a road on water. It could handle heavy traffic and could adjust to changing water levels as pontoons rode up and down with the current. These bridges were slower to construct than standard fixed spans, but provided crucial capability for very wide rivers. Railway bridges used modified Bailey panels. The British Army needed to restore railway lines in Italy and northwest Europe. Standard railway bridge equipment was even more cumbersome than road bridge equipment, so engineers adapted Bailey panels. Railway Bailey bridges used heavier transoms and stringers to handle train loads. The panels themselves were standard, but the supporting structure was reinforced. Rail was laid directly on the Bailey deck. These bridges carried trains successfully, though usually with speed restrictions. Specialized decking emerged for different conditions. Standard steel decking was heavy but durable. Timber decking was lighter and easier to source in remote areas. Pierced steel planking, metal sheets with holes to reduce weight while maintaining strength, became available later in the war and offered good performance with reduced weight. Pre-assembled sections reduced field construction time. Engineers could assemble multiple panels into larger sections at staging areas behind the front lines. These sections, perhaps consisting of 3-4 panels already connected, could be trucked to bridge sites and connected quickly. This approach reduced field assembly time but required more trucks for transport. The Bailey Bridge's impact extended far beyond World War II. After the war, thousands of Bailey bridges remained in service throughout Europe and Asia. Many stayed in place for years, serving as permanent infrastructure until replacement bridges could be built. European reconstruction relied heavily on Bailey bridges. Germany, France, Italy, Belgium, Netherlands, and other countries had thousands of demolished bridges. Rebuilding permanent bridges would take years. Bailey bridges provided immediate solutions. Some wartime Bailey bridges remained in service for decades. In remote areas where traffic loads were modest, there was no urgency to replace a perfectly functional Bailey bridge with a more expensive permanent structure. A few Bailey bridges erected in 1940–440, 5 remained in service into the 1980s and 1990s. Developing nations adopted Bailey bridge technology enthusiastically. The bridges offered several advantages for countries with limited infrastructure budgets. Low cost, Bailey components were relatively inexpensive compared to custom-designed bridges. Minimal equipment required. Installation needed no cranes or specialized equipment, critical in areas lacking such equipment. Unskilled labor. Local workers could be trained quickly to assemble Bailey bridges. Transportability. Components could reach remote areas by truck, even on poor roads. Flexibility. The modular system adapted to various situations. Countries in Africa, Asia, and Latin America used Bailey designs for rural infrastructure projects. A Bailey bridge could connect a remote village to a road network, enabling economic development and access to services, schools, medical care, markets. Military applications continued across the world. The U.S. military maintained Bailey bridge stocks through the Cold War. The medium girder bridge system, introduced in the 1960s, was essentially an updated Bailey bridge using lighter materials and slightly different connectors, but following Bailey's core principles. The British military continued using Bailey equipment, eventually developing the Mabey-Johnson bridge system, another Bailey derivative with improvements based on decades of experience. Modern British military bridge systems still trace their lineage directly to Bailey's 1940 design. Other nations developed their own versions. The Soviet Union created the MZ bridge system, similar to Bailey. China developed the 321 bridge, closely based on Bailey principles. India produces Bailey-type bridges domestically. The basic concept, modular panels, pin connections, hand assembly, proved so sound that it became a global standard. Civilian applications expanded considerably. Commercial bridge manufacturers began offering Bailey-style systems for civilian use. These modern versions incorporated improvements. Higher strength steel. Modern metallurgy produced stronger steels, allowing lighter panels with equivalent strength. Aluminum panels. For applications where weight was critical, aluminum panels offered substantial weight savings while maintaining adequate strength. Improved coatings. Modern corrosion protection exceeded WWII-era paint, extending service life. Standardized international specifications. Commercial Bailey-type bridges followed international standards, allowing easier procurement and use across borders. Modern Bailey-type bridges serve as temporary structures during permanent bridge construction. When an old bridge is demolished for replacement, a Bailey bridge can carry traffic while the new bridge is built. Emergency replacements after disasters. When floods, earthquakes, or other disasters destroy bridges, Bailey bridges can restore connections quickly. Permanent installations. In locations with modest traffic loads, Bailey bridges can serve as permanent structures, offering good performance at reasonable cost. Military applications. Armies worldwide continue using Bailey derivatives for tactical bridging. Engineering education uses Bailey bridges as a case study. Engineering students learn structural analysis using Bailey bridges as examples. The design illustrates fundamental principles. Load distribution in truss structures. The panel design demonstrates how triangulated frameworks efficiently carry loads. Connection design. The pin connections show how properly designed simple connections can handle large loads. Modular systems. Bailey bridges exemplify how standardization enables flexibility. Design constraints. The requirement that panels be man-portable demonstrates how constraints can drive innovation. Bailey's achievement lay not in inventing a new structural form, truss bridges were well established, but in reimagining how bridges could be manufactured, transported, and assembled. Several principles underlay his success. Standardization enables flexibility. By making all components identical, Bailey created a system that could adapt to any situation. The same panels built short bridges or long bridges, light bridges or heavy bridges. This counterintuitive result, that standardization creates flexibility, reflects deep design wisdom. Constraints drive innovation. Bailey faced severe constraints. Panels had to be man-portable. No specialized equipment could be required. Assembly had to be simple enough for minimally trained soldiers. These constraints forced creative solutions. If Bailey had been given unlimited resources and no constraints, he might have designed a more conventional and less useful system. Simplicity has value. The pin connections were almost primitive in their simplicity, a steel pin dropping through a hole. Yet this simple connection handled enormous loads reliably. Engineers sometimes assume complexity equals sophistication, but Bailey demonstrated that elegant simplicity can outperform complicated systems. Manufacturing matters. Bailey understood that a brilliant design that couldn't be manufactured in quantity had limited value. By designing for mass production from the start, he ensured his bridges could actually be built in the numbers required. User-centered design. Bailey designed for the actual users, soldiers in combat conditions, often under fire, frequently exhausted, rarely possessing specialized skills. By making the system simple enough for these users, he ensured its practical success. Modularity and scalability. The modular approach meant that supply was straightforward, more panels for bigger bridges. Logistics officers could calculate requirements precisely. This scalability was crucial for a system that needed to span rivers from 20 feet to 1,000+ feet wide. The mathematics of optimization. Bailey's 570-pound panel weight represented careful optimization. Lighter would sacrifice strength. Heavier would require more men or equipment. The specific weight was chosen to maximize the strength-to-portability ratio. These principles extend beyond bridge design. Modern engineers face similar challenges in many fields. Disaster response equipment must be transportable, operable by non-specialists, and rapidly deployable. Developing world infrastructure must be low-cost, low-tech, and maintainable with local resources. Military equipment must be rugged, reliable, and usable under extreme conditions. Modular construction systems in buildings, vehicles, and other products follow similar principles, standardized components combined in various configurations. Bailey's approach: identify the true requirements, design for the constraints, eliminate unnecessary complexity, enable mass production, focus on the actual users, remains relevant across engineering disciplines. Field Marshal Bernard Montgomery's assessment proved accurate. The Bailey Bridge ranks among World War II's most important innovations. While radar enabled defensive operations and aircraft struck targets, Bailey bridges kept armies moving, maintained supply lines, and enabled operations that would have otherwise stalled. The numbers tell part of the story. Allied forces erected thousands of Bailey bridges during the war, across North Africa, throughout Italy, across France and into Germany, throughout Burma and the Pacific Islands. These bridges carried millions of tons of supplies and equipment, enabling military operations on an unprecedented scale. But the broader significance lies in what Bailey demonstrated about engineering problem-solving. He took an apparently insoluble problem, how to bridge rivers rapidly under combat conditions with minimal equipment, and created a solution so straightforward it seems obvious in retrospect. Donald Bailey died on May 5, 1985, at age 83. He had been knighted in 1946 for his contribution to the war effort. His bridge design continued in service worldwide, testament to engineering principles that transcended their original context. Even today, 75 years after Bailey's first design, derivative bridges span rivers across the globe. The fundamental insight, that standardization and simplification enable rapid deployment, remains relevant. Modern engineers designing for rapid deployment, whether in disaster response, developing world infrastructure, or military applications, still follow principles Bailey articulated in 1940. The Bailey Bridge demonstrates what systematic engineering thinking can achieve, taking an apparently insoluble problem and creating a solution so straightforward that it seems obvious in retrospect. That, ultimately, is the mark of truly great design, not complexity that impresses specialists, but simplicity that works reliably under the most demanding conditions. When armies needed to cross rivers in an hour, Bailey gave them the tools to do exactly that. The bridges that spanned those rivers changed military history and demonstrated that democratic nations' industrial capacity, properly organized and intelligently applied, could achieve results that authoritarian systems with their rigid hierarchies could not match. Free engineers, working cooperatively with clearly defined problems and authority to innovate, outperformed command economies directed by ideological certainty. The lesson remains: underestimate democratic societies' capacity for practical innovation at your peril. Given a clear problem, adequate resources, and freedom to find solutions, free peoples produce remarkable results. Bailey's bridges proved it, one river crossing at a time, from Tunisia to the Rhine and beyond.